Hello students, so in the last class we started with triple integral, and we also looked into the basic definition and the concept of triple integral. We also started with one example which turned out to be a little bit long, so we stopped it in the midway. So we will continue with the similar example and we will try to finish it in this lecture, and then we will also look into some more examples motivated from triple integral. So we started with basically this example here. Evaluate I equals to x square plus y square plus z plus 1 whole square dx dy dz, which is basically the volume element, where the region is given by this here. So this one was basically our region of integration. So from here we calculated the range for z. So obviously the z is varying from 0 to 1 minus x minus y, because we start with all the points which are lying on the positive side of the z axis. Similarly, y will vary from 0 to 1 minus x, because we again start with the points which are lying on the positive side of y axis. And similarly we start our x will vary from 0 to 1, because we are starting for all the points which are lying on the positive side of x axis. So now that we have the limit, we can substitute for this for these values for on this region of integration. It's better to write e here just to signify that we are talking about a region. Now we have substituted the limits, as you can see here, and then we will integrate one by one. So first we will start with integrating with respect to variable z. So let's start with integrating with respect to variable z. So this is basically integral from 0 to 1 dx, integral from 0 to 1 minus x dy, and then integral from 0 to 1 minus x minus y, x plus y plus z plus 1 whole square dz. All right. So when we are integrating this integrand with respect to z, that means x and y are both treated as constant here. So because there is no x and y variable involving in this element dz. So that means we treat x, y, and of course 1 as a constant here, and then this is basically a plus x whole square integral. So for such integrals we know how to do the integration. So this will reduce to 1 by 3 x plus y plus z plus 1 whole cube, and then 0 to 1 minus x minus y. All right. So this will be the integral of this integration integration here. Now I take 1 by 3 out, and then this one is 0 to 1 dx, and then this is 0 to 1 minus x, and now we substitute the value. So when z is 1 minus x minus y, so then this will be basically 2, right? So 8 minus, when z is 0, then this is basically 1 plus x plus y whole to the power 3 dy. Now we integrate with respect to y only. So again, when we integrate with respect to y, then x will be treated as constant, and 1 and 8 are of course treated as constant. So we integrate. So let us integrate. Then this will be 8y minus 1 plus x plus y to the power 4 divided by 4, integral from 0 to 1 minus x dx. All right. And then we substitute the value. So this will be basically 0 to 1 8 1 minus x minus 1 by 4. This will be, if I substitute 1 minus x, then 2 to the power 4, and then minus minus plus. This will be 1 plus x divided by 4 whole to the power 4 dx. All right. So we will basically obtain, after simplification, we will basically obtain 1 by 3 4x minus 4x square plus 1 by 20 x plus 1 to the power 5 integral sorry, the value of the function of the integral evaluated at 0 to 1. So, here basically we calculate 1 plus x to the power 4 using the binomial theorem. So, it will be x to the power 4 plus 4 x to the power 3 and so on, and then we integrate with respect to x. So, this is a fairly easy how to say integral to evaluate. So, I am pretty sure you can be able to do this integral because it is basically an algebraic expression, and after you do the integration you will obtain a result like this, and then we substitute the value and it will result in 1 by 60 times 32 minus 1. So, basically 31 by 16. So, that is the value of this integral evaluated between this region actually. So, here first we had to find out the range for the variable x, y and z, and afterwards we just integrated with respect to z first, with respect to y second, and then with respect to z x third. So, this is the order which is preferred by most of the people. So, they initially try with integrating with respect to z and then y and then x. So, we will work out few more examples for you to get accustomed with triple integral. So, let us go to our second example. All right. So, the second example is evaluate. So, evaluate I equals to integral over the region E x square plus y square plus z square dx dy dz over the sphere x square plus y square plus z square is less or equal to a square. So, we have to evaluate this integral here. So, that is the integrand basically. So, this integral here over the region E, and this region E is basically that sphere which is of course, a bounded domain when A is finite. And if we want to draw this sphere, so I am not a really good at drawing. So, this is basically 0, y, z and x. So, that is my radius A, and this is this rectangular this is this region E where we have to perform the integral. So, now in this region if we substitute, so let us substitute x equals to r cos theta cos phi, y equals to r sin theta. Okay, we will start with r sin theta cos phi, r sin theta sin phi, and z equals to r cos theta. So, if we take square of x square plus y square plus z square, then this will actually reduce to this sphere x square plus y square plus z square equals to a square. Now, to do the change of variables, actually we know that we need to calculate the Jacobian. So, for the function of two variable, the Jacobian was given as del x y del u del v. So, for that was for the function of two variable. Now, if we want to have the Jacobian for the function of three variable, then in that case we basically write x y z and then del u del u v and w. So, this is how to say a standard way of converting a change of converting a function of one variable to a function of second variable in the integral, and in order to do that we need to calculate the Jacobian, which is given in this fashion. So, this is basically del x del u del x del v del x del w, and then we have del y del u del y del v del y, del w, then del z, del u, del z, del v, del z, del w. Now, here u is basically r, v is basically theta, and z is basically phi. So, if we differentiate x, y and z with respect to r, theta and phi, then basically we can calculate this whole determinant, and it will result in r square sin theta. So, this task is very simple, and therefore, I leave this one to the students to calculate. So, we will basically obtain r square sin theta, and therefore, I can write my integral I over the region E x square plus y square plus z square dx dy dz. So, if I transform this integral into a polar one, then in that case this will be r running from 0 to a, because that is what our that's the range for the variable r or the radius, and theta will run from 0 to pi and phi will run from 0 to 2 pi, all right, and this will be x square plus y square plus z square. So, if I substitute for x r square r sin theta cos phi, then it will be r square sin square theta cos square phi, and similarly for y it will be r square sin square theta sin square phi, and then z will be r square cos square theta. So, we substitute all those things, and then this will be reduced to r square times determinant of z dr d theta, determinant of z dr d theta d phi, and then this will be r running from 0 to a, theta running from 0 to pi, and phi running from 0 to 2 pi. This is r square, and determinant of j is r square sin theta dr d theta d phi, and then this whole thing will reduce to integral r running from 0 to a, theta running from 0 to pi, and phi running from 0 to 2 pi, r square sin theta dr d theta d phi. So, the same thing here, and now we integrate with respect to phi first. So, we integrate with respect to phi, and then this will be phi. So, the value of phi will be 2 pi basically. So, I am taking that 2 pi outside, and then here we will have dr d theta. Next, we will integrate with respect to theta first, and then in that case this will reduce to minus of cos theta. So, here let us write r running from a to pi. When we integrate with respect to theta first, it will be so r square. So, sorry, we will have r to the power 4, right? Yes. So, r to the power 4, and when we integrate with respect to theta, then this will be minus of cos theta. Theta will vary from 0 to pi d theta, dr, and when cos theta when theta is pi, then cos pi is minus 1, then this one will be plus 1, and this one will be cos 0. So, cos 0 is 1, and then minus plus. So, this will again be 4 pi times integral from 0 to a r to the power 4 dr, and when we integrate this one, then this will be 4 pi r to the power 5 by 5 r running from 0 to a. So, this will be 4 by 5 pi a to the power 5. 4 by 5 pi a to the power 5. So, this is the required answer for the integral, for the triple integral which we started with, and we can see that. So, here we can see that we were given a bounded region first of all. So, from the bounded region, it is also very convenient to use spherical polar coordinate system. So, here we have a sphere basically, and for this sphere we can use the spherical polar coordinate substitution. So, that is r sin theta cos phi, r sin theta sin phi, and r cos theta. Of course, this point lies on this sphere. Now, we substitute so next we calculate the Jacobian, and while we have the Jacobian value, we can do the change a variable or transformation, and by changing the variable we have next new variable as dr d theta d phi, and then here you will have a Jacobian j, and just substitute the value of the Jacobian and then integrate with respect to phi first, then with respect to theta, and then with respect to r, and that will be our required answer. And this is the area which is basically bounded by this is the the value of the integrand given bounded by that region or that sphere x square plus y square plus z square is less or equal to a square. So, this was one such example of triple integral. Similarly, we can also have example of type let us say example 3, evaluate where V is the sphere is it 1? Yes. So, now again here we are given a sphere which is basically again a bounded sphere. So, a bounded region we have in our hand, and we need to evaluate this integral here. So, the integral I is given by integral over v x square dx dy dz, and obviously v is a bounded region where x, y, and z can be transformed into a spherical polar coordinate system. So, we can have x equals to r sin theta sin phi sin theta cos phi or sin theta sin phi like here. So, sin theta cos phi and then sin theta sin phi. Okay, we can also take that one. So, sin theta cos phi, we can take sin theta cos phi, and then y equals to r sin theta sin phi, and then z is r cos theta. So, now we can have dx dy dz calculated. Then on the right hand side we will have dr d theta and d phi calculated, and we substitute the value of x here which is r square sin square theta cos square phi. So, ultimately this whole thing will reduce to r varying from 0 to 1, and theta is varying from 0 to pi, and phi is varying from 0 to 2 pi. Then we have x square, which is basically r square sin square theta cos square phi, and then dx dy dz, which can be transformed into determinant of j dr d theta and d phi. All right. So, now we can calculate this Jacobian here. So, in order to calculate this Jacobian, we will do the similar trick what we did in the previous example, and this will be basically r square sin theta. Was it the same thing? Yes. So, we will obtain r square sin theta. So, substitute the value of r square sin theta, and then this whole thing will reduce to basically a trigonometrical expression. So, this whole thing will reduce to basically a trigonometrical expression, and then we just integrate with respect to phi first, and then with respect to theta, and then with respect to r. So, let us try to do that. So, what we do, we first separate the function phi. So, cos square phi d phi, and then integral from theta running from 0 to 2 pi 0 to pi. sine square theta d theta, and if we integrate with respect to r first, then this will be 1 by r to the power 5, 0 to 1, and then I will have a 1 by 5 here, and this is basically dr. So this is basically d theta d phi. So this is basically so what we have here. So we have r square sine theta. So we have r square sine theta. So this will be sine cube, and we will have So we will have 1 by 5 r to the power 5. So 1 by 5 is already outside. So we will have r to the power 5. All right. So now we do substitution for r equals to 0 and r equals to 1. So this term will remain as it is, and then here we will have integral from 0 to 2 pi cos square phi d phi integral from theta running from 0 to pi sine cube theta d theta. Here we can either use the induction formula, or we can use the trigonometrical formula, where this will reduce to sine 3 theta minus 3 sine theta, and from there we can do some calculation, and we can be able to find out the value of this integral with respect to theta, and then we integrate, then we adjust a factor 2 here, so that we will get 2 cos square phi, and then we can write 1 minus 2 cos square phi is cos 2 phi minus 1, cos 2 phi plus 1, and from there we can be able to calculate this integral as well, or we can use the induction formula. So on both of them we can either use the induction formula or use our traditional cos 2 phi sine 3 phi results, and then after doing the simplification, we can be able to obtain 8 by 5 times 1 by 2 times pi by 2 times 2 by 3. So this is basically 4 pi by 15, and this is the required answer of our problem. Where is that? This here. So here the given integrand was x square times dx dy dz. So basically doing this simple method of substitution, we can be able to reduce the whole integral into a rather simpler one, and then we just use some trigonometrical formula like cos 2 theta, sin 2 theta, cos 3 theta and all, and that will give us the required value of this integral, because now we are integrating basically two different integrals because of their integrand. So this one we can do that at home, and this one also we can do that basically by ourselves, and just how to say, writing cos 2 phi cos square phi as as that formula expression of cos 2 phi plus 1, and we can write sine to the sine cube theta as sine 3 theta formula. We can be able to calculate these two integrals separately, and then substitute them, and that will give you the answer. So once you reduce them to a trigonometrical form, it's not that difficult. All right, and this was the second example, or third example basically, which we covered. We can work out one more example if we have some time. So let's consider another example. So another example could be without having to reduce it into a trigonometrical form, could be so we can start with okay, let's consider this problem here. So example 3, evaluate I equals to integral over the region R 1 minus x square minus y square minus z square dx dy dz, where R is the region interior to the sphere x square plus y square plus z square equals to 1. So solution, here also what we will do basically is R is the region which is the interior of this sphere. So, again the region R is bounded by this sphere S here, let us say. So, we can draw the, so this is our z axis, this is our y axis, this is our x axis, and that is my sphere, this is the radius 1, and this whole is the region R. So, this is the region R, and if we substitute again x equals to r sin theta cos phi, y r sin theta cos phi, y equals to r sin theta sin phi, and z equals to r cos theta, then this will basically this integral I equals to integral over the region R 1 minus x square minus y square minus z square dx dy dz. So, when we are transforming it into a how to say spherical polar coordinate system, our r will run from 0 to 1, theta will run from 0 to pi, and phi will run from 0 to 2 pi. Then we substitute for x, y, x, y and z, and here basically the value of the integral. So, when we substitute r equals to cos square theta, r equals to sin square, r equals to when we substitute x equals to r square sin square theta cos square phi, and y equals to so the value of this integrand basically will be 0. So, this here, so this problem will not be that much how to say interesting for us. So, what we can do is we can impose conditions like x greater or equal to 0, y greater or equal to 0, and z greater or equal to 0. Then in that case we are actually in the first quadrant, and then for the first quadrant we can have theta running from 0 to pi by 2, and theta running from 0 to pi by 2, and phi will run from again 0 to pi by 2, whereas r running from 0 to 1, and then this will be 1 minus r square dx dy Jacobian of j dr d theta d phi. So, we just made the problem a little bit more interesting by imposing these three conditions. So, if we impose these three conditions, that means x will lie in the first quadrant, y will lie again in the second quadrant, and z will also lie in the so y will also lie in the first quadrant, and z will also lie in the first quadrant. So, that means they are both lying in the positive quadrant of x, y and z axis, and then in that case theta will go from 0 to 2 pi, and phi will also go from 0 to 2 pi. So, that's what we have written here. And now this Jacobian we know that is basically r square sin theta. So, let us write that, and this will be integral from 0 to 1, theta will be from 0 to pi by 2, and phi will be from 0 to pi by 2 r square sin theta square root of 1 minus r square dr d theta d phi. And now we can evaluate these three integrals. So, basically the triple integral one by one. So, what we can do, we can write integral 0 to pi by 2 d phi, and then integral from 0 to pi by 2 sin theta d theta, and then integral from 0 to 1 r square 1 minus r square dr. So, this is what we will get, and we can calculate this one from our usual trigonometrical results. So, we again substitute r equals to sine I don't know t, and then from there we can try to calculate this this function, this integral here. Calculating these two would not be difficult. So, this one is basically pi by 2 and this one is minus cos theta. So, cos pi by 2 is 0. So, this basically will give us 1. So, the value of this integral is 1, this one is pi by 2, and the calculation of this one should be fairly easy using some trigonometrical results, and ultimately we will obtain the value as pi by 2 times 1 by 4 times 1 by, so pi by 2, this one is 1 and this one is just, you just calculate the value and substitute here, that will give us the required value. So, this is pi by 2, this is 1, and you have to calculate the value of this part to substitute here, and that will be the answer of this integral. So, I am leaving the calculation up to the students because it is a very fair simple example. So, here in this case also our given region of integration was this sphere bounded by 3 other conditions, that all the points should lie on the positive side of x axis, y axis and z axis. That means we are in the first quadrant, and therefore, your r, theta and phi would vary from 0 to 1, pi by 2 and pi by 2 respectively, and then we just substituted the values for x, y, z using spherical polar coordinate system, and then we just have to do this simple calculation. So, and that will give you the required answer. So, here again in this example we saw that how we calculate the triple integral on a bounded region, and we can also work out several examples of this type. All you have to do is to find out the region or the domain for the variables x, y and z, for which we can do the integral actually. And once you have the region, then doing the integral or performing the triple integral would be fairly easy, as we saw in these examples. So, we will try to include some more examples in your assignment sheet, so that you can be able to practice them and be perfect at them. And we will stop our triple integral part here, and in the next class we will start with our area of plane regions. So, thank you for your attention today, and I will look forward to you in the next class.